Today we will discuss about the optical fiber. But before going to start, let us try to know that what are the demerits of communications with coaxial cables, or what are the limitations of coaxial cables. But we should know what is communication. Do you know communication? Communication is transferring the data from one place to the other place. Now, this in the communication system, probably all of you know that at first the signal is modulated and then it is demodulated at the receiver's end. So at the transmitter end, the signal is modulated. Modulated means if a signal is there that is superposed to the carrier wave should have the high. There are two types of modulations, probably all of you know that: frequency modulation as well as amplitude modulation. So after that signal is sent to the receiver end, and at the receiver end the segregation of these two happens. Due to this segregation, the actual signal got separated. This is called as demodulation. So here we are trying to find out that what is the limitation of a coaxial cable. Now what we know that first limitation which can be enlisted is less bandwidth. The bandwidth of the coaxial cable is very less, that is 500 megahertz. Because of less bandwidth, less number of channels are available, so less amount of information can be processed. Second is large size and heavy weight. The size of the coaxial cable is high, and because of this large size the weight becomes heavy. So feed the data through this coaxial cable, then we will have to afford the large size and heavy weight. Not only that, these coaxial cable are of maximum 1 kilometer or 2 kilometer. If you will have to communicate for a longer distance, then it is not possible to communicate with a single coaxial cable. Thirdly, the interference. If you ask to your father and grandfather, they will certainly tell you that just before 20 to 30 years ago, how the TV transmission was going on, how the radio transmission was going on. Actually what happens, there were interference, and because of that the voice and pictures were not clear. You ask them about the landline phones, they will certainly tell you that there were cross-talkings. This cross-talking is what? This cross-talking is due to the interference. Third, cross-talking is due to the interference. If there will be interference, then the voice of two group of peoples got interconnected. Now the fourth, which is the chief demerit, that is losses. In the coaxial cables, the signal which is given as input, that signal never comes out. There is greater loss. So if coaxial cable is used to communicate for a longer distance, then signal quality will become degraded at the receiver's end. There are different types of losses: absorption loss, scattering loss. Other than that, the coaxial cable got affected due to rusting. So due to that there will be different types of losses, and the signal will be lost to a large extent, due to which we will see the attenuation. So these are the different problems which we used to see in coaxial cables. Now about the radio waves communication. If in the electronic We know that the radio waves are used to communicate the signal from one place to the other place or from one device to the other device. The frequency of radio waves is 10 power 6 hertz. Now, if the frequency of the radio waves is 10 power 6 hertz, in contrast to the frequency of the light wave, which is 10 to the power 14 hertz to 10 to the power 16 hertz, what we know that it is a well established fact that if the frequency is higher, the number of channels will be higher, and because of that, large amount of data can be communicated from one place to the other place. Just I talked to you about the coaxial cables. In the coaxial cables, if you want to transmit more amount of data, that is not possible with a single coaxial cable. This is because of the fact that the are less, and these channels are less because of the less bandwidth. But here in the radio waves, the number of bandwidth is greater because of frequency, whereas in light waves it will be more and more than the radio waves. That is why if light waves are used to communicate, then we will get large number of bandwidth. We will get the large number of channels because of high bandwidth, and if bandwidth will be high, number of channels will be high, then the large amount of data can be processed and communicated from one place to the other. As in the last slide, we come to know that if in place of radio waves we use the light waves for transmitting the signal from one place to the other place, then it will, due to its high bandwidth, it will contains large amount of without destruction or without distortion. There will not be any attenuation, and this is realized in optical fibers. Optical fibers are having three layers. The innermost layer or innermost part of the optical fiber is called as core, as shown in the diagram, and over that there is cladding, and the outer layer is called as jacket or sheath. Now the signal is guided through the core. Actually what happens, the signal is sent from one place to the other place guidedly. How this can be done? If you recall the total internal reflection, then you will be able to know. That we'll discuss in the next slide. In this slide I am telling you that the refractive index of the core is higher than the refractive index of the cladding, and the refractive index of the cladding is higher than the refractive index of the jacket or sheath. Now the dimensions. The dimension of the core is from 25 micrometer to 62.5 micrometer, whereas the dimension of cladding is 125 micrometer. The dimension of the sheath or jacket is 250 micrometer. So what we can say that the dimension of the core runs from 25 micrometer to 100 micrometer. The dimension of cladding runs from 100 micrometer to 125 micrometer, and the dimension of jacket or sheath is from 125 micrometer to 250 micrometer. Principle of optical fiber, or how the light propagates in optical fiber. The principle of optical fiber is total internal reflection. The light is passed from one end of the optical fiber to the other end of the optical fiber guidedly using the principle of total internal reflection. As you see in the figure on the slide, the blue lines are the boundaries of core, and beyond that there is cladding. Now, just in the last slide I told you that the refractive index of the core is taken higher than the refractive index of the cladding. Because of that, the core is treated as the denser medium with respect to the cladding. Now, if this, then the light, when the light is falling at the aperture of the optical fiber, what will happen? The light will go guidedly. Suppose many number of or a large number of lights can propagate, which are carriers of the signals from one part of the optical fiber to the other part. For simplicity, we have taken only two rays, red and blue rays. Now in this red ray, suppose for the red ray, the light is allowed to fall at a special angle on the aperture. What this special angle is called, that we will discuss in later slides. But here you can think it that the light is allowed to fall over the glancing angle. Now it will suffer refraction, and following the rules of refraction, this light will allowed to fall on the boundary of the core, or you can say that interface of core cladding. Now at this core cladding interface, if the angle of incidence is greater than the critical angle, then what will happen? Just recall critical angle. What happens that total internal reflection is seen only when the light is passing from denser medium to the rarer medium. So if the angle of incidence at the denser and rarer medium is greater than the critical angle, then light will not refract, rather than that it will be reflected back in the same medium. So here also that will happen. You see the red line which shows a light wave. If this is allowed to fall over the optical fiber, it suffers the refraction and then it is falling over the core cladding interface. Here, if the angle of incidence is greater than the critical angle, then it will not be transmitted cladding, rather than that it will be reflected back to the core. Again, this wave of light is, or ray of light is falling at an angle greater than the critical angle at the interface. Because of that, again it will be reflected back in the same medium. So because of that, using this property, or you can say that due to the multiple total internal reflections, the light will not go out from the core, rather than that it will be totally internally reflected in the same medium, that is core, and reach to the receiver's end, due to which there will not be any distortion in the signal, there will not be any attenuation, there will not be any loss, and the whole signal which is given as the input, that will comes out as output, and we will get the total signal at the receiver's end guidedly. You can also view this in the animation which is given on the right side of this slide. Angle of acceptance. Now we know that in the optical fiber, every signal which is falling on the optical fiber never reaches to the receiver's end. Those signals for which the total internal reflection is seen, that will be only reached to the receiver's end. For that, what we require? We require that the signal should fall on the greater angle than the critical angle at the core cladding interface. Then only it will be totally internally reflected in the core, and it will not leave the medium, or it will not go outside the core to the cladding. So the angle at which the signal is launched or allowed to fall on the optical fiber, that the signal suffers the total internal reflection and it reached to the receiver's end, is called as the angle of acceptance. So angle of acceptance can be defined as the angle at which, if the light of suitable wavelength is allowed to fall over the aperture of the optical fiber, then it will suffer the total internal reflection and carry out the total information from one part of the optical fiber to the other part without any distortion. As in the figure, it is theta naught. Theta naught is the angle of acceptance. Now next is numerical aperture. What is numerical aperture? Numerical aperture is defined as the sign of angle of acceptance. So here angle of acceptance is theta naught. Because of that, the numerical aperture will be sign of theta naught. As if you look in the diagram shown on the screen, you will find that we have taken the refractive indices of core, cladding and as N1 and N2 respectively, where the refractive index of core is greater than N2, that is N1 is greater than N2. Now let us suppose the refractive index of the outer medium, that is air, is N0. Then we will be able to derive the formula for numerical aperture, that we will discuss in the next slide.